Jemima, who's presenting a project on solar sails.
Basically, the basis of our project is spacecraft that observe space weather, essentially. And it's important to know about space weather because it can affect power grids and radio communications on Earth. And at the moment, the spacecraft that look at space weather are all at this point in space called L1. And that's because if you put a spacecraft there, during the orbit of the Earth around the Sun, the satellite will stay in that position between the Sun and the Earth, in theory, and it will move with them. And that means that because the Sun is the main source of space weather, you'll be able to let the Earth know about any incoming space weather that can affect it. So that's the basis. What this project is about is increasing the warning time for space weather, increasing the warning time the Earth gets about space weather. So to do that, you would need to move the spacecraft closer in towards the Sun. And a way you can do that is using a solar sail, because when you use a solar sail, the momentum from the photons hitting the solar sail causes a force in the opposite direction to the Sun, so that can balance an increase in gravitational potential energy when you move from the Sun, when you move the sail closer to that. So you can basically create an artificial Lagrange point closer to the Sun. So that's what we're looking at for the project. The first thing we had to do is find out where the natural L1 is. And these two graphs here are just looking at that. The first one is the bird's eye view of the system with the Sun, Earth and satellite, and you can see what's going on a lot more clearly on this graph, because this is the displacement of the Earth with respect to the Sun over almost a whole year, and this is the displacement of the satellite with respect to the Sun, again over almost a whole year. And what we can see is the motion of the satellite is mimicking the motion of the Earth, which suggests it's at L1. Behaviour you wouldn't want on this graph if you were trying to get at L1 would be the satellite having regular peaks like that, because that would suggest it's orbiting the Earth, or the satellite flying off in some direction that's not mimicking the Earth's trajectory, because that suggests it's just moving off on its own. So that was just a natural L1. Then we had to find the artificial L1, and we started just by building in an idealized solar sail, which is where we get this graph from. As you change the area of the solar sail, you would get an increased number of photons hitting it because of the greater area. So that would mean a greater force in the direction away from the Sun. So you'd be able to get it closer to the Sun with a larger area. So this is what this graph shows. And this goes up to 300,000 meters squared. But at the moment, the projects that are either in space or being talked about are much smaller. There is a project called Icarus from Japan, and that is only 14 meters by 14 meters. And the Sunjammer project, which is actually one of the bases for this project, was going to be 38 meters by 38 meters, which is only 1,444 meters squared, which, well, this project isn't going ahead, but that's quite a lot smaller than some of the ones we've trialed for. The important thing to note is when you get to an area greater than 400,000 with this code, you can't actually find a point of stability where you can leave the spacecraft and it'll act like an artificial L1, because when the area is greater than 400,000, the spacecraft always flies off from what we've tried. The final thing we looked at was sail degradation, because that affects the lifetime of the sail. The first graph here looks at the acceleration of the spacecraft over a time of 2 years, depending on the degradation constant. The top line here is just what an idealized solar sail would be, and you can see that for a a degradation constant of 0.1, which isn't too large, it does actually decrease significantly. So we do need to look at ways to minimize that. And one way we looked at was changing the sail pitch angles of the solar sail. At the moment, for this graph and this graph, the solar sail has been directly facing the sun at all times. But what we were looking at in this graph is what would happen if we move the solar sail at an angle like this. And what does happen is the degradation constant has less of an effect, as you can see by the clumping of the blue lines where the sail pitch angle is 45 degrees compared to here when the red lines when it's facing the sun head on. But one thing you do need to take into account with that is that the acceleration of the spacecraft for the 45 degree angle is much lower than the acceleration of the spacecraft when it's facing the sun head on. So that suggests that there is an optimum angle where you'll get a sufficiently high acceleration and be able to minimize degradation for a certain distance. So that's something that people need to take into account when they're making solar sails, or that's what this suggests. So that's about it for the project. Our main focuses were the design and the lifetime of the sail. Had we had time, we would have liked to explore it more, but unfortunately not.